So I drew this handy dandy mechanism here with those double-sided arrows. And so first of all, I want you guys to tell me, if it would zoom. All right. So this set of arrows, if we go from an alcohol to an aldehyde, what do we get? Or what reaction are we doing? Excuse me. Oxidation or reduction? Cool. Everyone said. Sorry, did someone else say something?
No, I was just saying oxidation.
Okay, perfect. So yes, it's oxidation, and I'm just gonna write OX because it's easier. And then if we go the other way around, what does it have to be? Reduction. Cool. And
I just have a quick question. This is something I do to just kind of remember. I'm not sure if it's correct. I kind of have oxidation, and just to kind of make it a little easier for me, oxidation is when the hydrogen is removed, and reduction is when the hydrogen is added. Is that like an easy?
Yes, that is definitely a valid way to think about it. For the purposes of this class, though. So just a little asterisk. Yes, you can think about it that way. But when you go to other classes, like if you choose to do higher levels of chemistry or whatever, the rules are a little bit more broad than that. But for the purposes of this class, yes, that's absolutely valid.
Okay.
Okay, cool. All right. And also in my head, I don't know why oxidation is red and reduction is blue, but I'll always be color coding it that way. And all right. I'm not going to make you guys answer this again because I'm sure that you can agree if this was oxidation, this is also going to be oxidation. And if this was reduction, this reaction will also be reduction. So I'll just go ahead and fill that in for you. And all right, someone asked a question in the chat and I'm going to kind of answer it in the broader way. So oxidation is essentially adding more bonds to oxygen. Technically, the definition is to any electronegative atom, but for the purposes of this class, we're just going to use oxygen. And then reduction is the exact opposite. So we can think of it as someone mentioned as adding more bonds to hydrogen. And I'll zoom out so you guys can see that all at once. Any questions on the super general oxidation reduction stuff? Okay, cool. And I'm sure this is going to sound silly to you guys, but I'm just going to write it in the corner. So I always think about it in the terms of Leo goes. And it's, or oil rig. I personally don't like oil rig, but either way, it doesn't matter. So in an oxidation reaction, you are going to have electrons, you're losing electrons. In a reduction reaction, you are gaining electrons. And with that, I want to mention the oxidizing agent will be reduced. And, excuse me, the reducing agent is oxidized. It's not a super difficult concept. It's just something that I like to point out because sometimes the wording can become confusing. Any questions about the general information about oxidation and reduction? Also, while you guys are thinking, it is officially fall, and fall is my favorite time of the year, like by far. So starting next week, I am going to be full on fall craziness. Like if you thought these handout decorations were a lot, just wait until next week. We're getting straight up spooky. It's gonna be great. Anyways, I just made myself really excited. So anywho's, going on to oxidations, we've already done this, so I'm just gonna do a really quick recap, and I'm gonna ask you guys questions. So if we are going from or you know what? Let's practice this skill first. Primary, secondary, what is this? Unless you guys can't see my screen.
What's your question?
Was the first alcohol primary, secondary, or tertiary? But I already wrote primary. But what about the second one? What do you think?
No, it's not an alcohol, but it's primary too, no?
This one.
Oh, this one. Not primary.
Yeah, it was the same thing. I was your question.
Okay.
Okay, so this is secondary. And I didn't draw tertiary. Why not?
Because there's no reaction.
Exactly, because tertiary will not undergo oxidation. Sweet. You guys are listening and paying attention. I love it. You guys are awesome. All right, so what is the difference between the first reaction and the second reaction?
Wait, can you mute your mic, please, if you're not going to talk?
Oh, yes, please. I think one person. There we go. Awesome. So, guys, oh, someone already answered. Strong versus weak. Yes. How do you know one of them is strong and one of them is weak? Oh, wait a second. I got too excited. One makes an aldehyde versus the other one goes all the way to a carboxylic acid. Awesome. So this first one is going to be a strong oxidizing agent, and I'm just going to write it as O. And we know that because it doesn't stop at the aldehyde. It goes one more time to make a carboxylic acid, versus the second one has to be weak because we are stopping at the aldehyde. For secondary, what did we use? Strong or weak? Either. I'm so proud of you guys. You like know all my trick questions. Amazing. So either works because it is secondary, and that means that we only have this one hydrogen right here to get rid of. And once we get rid of that, we make a ketone, and we can't go anywhere from there because we're not going to break any carbons or anything. And yeah, that's pretty much it for reaction mechanism stuff. You don't need to know any mechanisms, just starting material and product. But then for oxidizing agents, someone tell me what was the clue I gave you guys for a really easy way to distinguish strong versus weak.
If it has more than 4 oxygens.
Yes. Okay. Awesome. For oxidizing agents, we're going to write a little note next to strong. 4 or more oxygens. You're absolutely 100% correct. And that makes sense because if we want to oxidize, we want more oxygens. So out of these, the only ones that are going to be weak are PCC and the DMSO one. I'm not going to rewrite the whole thing just because it's already there for you guys. And then strong will be everything else. I could have not rewritten it, but I've already committed, so I guess that's happening.
I just have a question. The DMSO, COCl, that's part of it's part of DMSO? Or?
Yes, so that's all one reaction. It's just going to be different steps.
Oh, okay, gotcha.
The only exception to the 4 or more rule is this one, but it almost never comes up. I just put it in there because I noticed it was in his lecture. But for the most part, that's an outlier. And if you know the 4 or more rule, you're good to go. And I'll zoom out so you guys can take a picture or do whatever you want. And while I do that, I am also going to mention that the handout has not been posted yet. If you weren't here when I said that, it will be posted soon. I just am having trouble getting access to your Canvas page for some reason. If I can't post it today, I will email you guys later. I don't want you to suffer or anything.
I have a question.
Yes, please. What's up?
Oh, wait. Actually, I'm going to say, is it 3 or more oxygen or 4 or more? But it says 4 or more right there.
Yep. The reason it's not 3 or more, even though that one technically has 3, there's a different rule for 3 oxygens, which I'll bring up in a second. But yeah, good question. Oh, you didn't see that at all. Actually, you guys probably have some advantage to being online because I used to accidentally throw markers at people. And so now when I accidentally throw my pen, it doesn't hit anyone. That's half a joke. All right, so I don't see any other questions or anything, so I'm going to move on. If my internet wasn't so stupid, that'd be awesome. Okay, you guys can still see the screen, right? For me, it's frozen, but I don't know if you guys can still see it. Okay, I'm going to go on, and hopefully you can. So before we go into reduction, something you have to take note of is reactivity of carbonyl groups. So what is something that goes into reactivity, like affects reactivity, I guess I should say? And if you guys, wow, you guys are giving me a lot more in-depth answers than I was expecting. Someone said stuff. Yes. Okay, so one person said the answer I was looking for. Well, all of these things are correct. If you watched my chapter 9 videos, what was that thing that I told you is always the answer? There were 2 things. We talked about it for chemical shift. Someone said symmetry, yes, but no. One of them was sterics. Someone said that. The other one was electronics. Yes, okay. So sterics and electronics are what we're looking at. Yay. So what does this mean? Essentially, you know what, before I tell you, my next question to you guys is, are we looking for it to be a good nucleophile or it to be a good electrophile?
No. I was saying, doesn't it have to be a good nucleophile?
Why do you think
Well, because are we not gonna see those in reactions? Good nucleophiles, so that we can like make like good leaving groups, and I don't know what I'm saying at this point.
I kind of get what you were saying, but we're gonna say it's a good electrophile because the carbonyl is like 9 times out of 10 gonna be the electrophile. Yes, we're gonna do a lot of reactions where we activate it and the oxygen will take a hydrogen and become protonated, but that's not what I'm talking about. For the most part, something attacking the carbonyl carbon, and then our reaction will proceed. So we want a good electrophile.
Okay.
So in reference to sterics and electronics, do you want more stuff around the carbonyl carbon or less?
Less.
Less. Awesome. So you want it to be less sterically hindered. So between all of these, what is the most obvious one that has like the least steric hindrance between all of them?
The oxygen by itself, the ketone.
Close. So we're going to consider. Okay, let me think about how I want to say it. All right. So we're going to consider these in like two groups, right? So we're going to say that the ketone and the aldehyde are part of group 1, and then the carboxylic acid and the ester are in group 2, right? I'll write that down in a second, but I want you to think about it in your brain first. So between the ketone and the aldehyde, we know that the one that has the least steric hindrance is going to be the most reactive. And as some people said in the chat, there are 2 CH3s here, and there's only 1 CH3 here, so the aldehyde will be the most reactive. And we can use electronics to double check our answer, because what did we, and someone said it in the chat a while ago, hyperconjugation. That was awesome that you knew that. I was very impressed. If you don't know what it is, don't worry about it. All you have to know is that the CH3 groups are going to donate electron density, right? And to be an electrophile, do we want more or less electron density? Less, exactly. Ooh, we actually have a 50-50. So the reason we want less is because we want a more positive charge. And in this, we already have a delta minus and a delta plus. And the more electron density we get, the less of a delta plus we have. So the more positive, the better. So that is why this one is the most reactive, and I'm going to say number 1 for most reactive. And then we know that this will be number 2. The reason both of these are more reactive than the 2 carboxylic acid derivatives is because the oxygen is super electronegative, and it just obviously takes up a lot of space. So no, we don't like that. But between the 2 of them, what do you guys think? Do you have any opinions? Which one do you think is more or less reactive?
I feel like the one with the R group that has less resonance than the one with the alcohol, the carboxyl group.
Okay, that's a good idea, but why do you think it would have less resonance?
Well, the movement of like electrons, the way we learn, so you can move the electron on the alcohol, and then sort of move it to the and then move it up here.
Yeah,
I can't really explain it without showing.
That is true, but you could also do the same thing here. The R group wouldn't really have an effect.
Okay, so would the alcohol have like it would be more soluble? Does that have to do anything with reactivity? Yeah.
Not really.
It would react? No. Okay.
It's actually kind of a trick question, and I'm sorry, but this is where I get my joy. So these 2 are very, very, very close in reactivity. This one is number 3, and this one is number 4, but they're so close that they're almost equal. So yeah, I just wanted to have some fun. I apologize if I caused anyone any emotional distress.
Wait, I have a question.
Yes.
Can you repeat how the other topic that you were talking about that you put on the right side affects reactivity?
Yes. So, like, let's say we're going to just use these 3 for now. I'm going to erase all my green stuff. So the 2 main factors are sterics and electronics, right? So if we're talking about steric hindrance, we know that here we have a carbon group, a hydrogen, a carbon and an oxygen, a carbon and a carbon. Obviously, hydrogens are the least sterically hindered group we can have because they're just that one tiny little speck. They don't really do much. So between the ketone and the aldehyde, this carbon group will be much more sterically hindered than this hydrogen. So we know that the aldehyde is more reactive because of steric effects. If we think about electronic effects, we have the electron density being donated through electronic effects from the CH3 groups. So in the case of the aldehyde, we have one electron donating group. Here we have two electron donating groups. And so since we want the most positive charge possible on that carbonyl carbon, the less groups we have that donate electron density, the more reactive it will be. So that's why the aldehyde is number one. And then between the ester and the carbonyl, I don't think we've gone actually to esters. So I'm so sorry if I didn't tell you what an ester is and I just assumed you knew it. An ester looks like this, what I've already drawn, and the R group can be replaced with any carbon chain. I'm very sorry. I just completely forgot that that wasn't covered in Orgo 1. But back to what I was saying. So between the carbon and the oxygen, we know that the oxygen is huge. It has a huge electron density. It's so big in space. So it is going to be much more sterically hindered. Plus, when we're talking about electronic effects, let's do our resonance. So not only do we have this like weakly donating group, we also have like straight up resonance going on. So the electron density is going in this area that I'm showing, the blue path that I'm drawing. And that means that we have a lot more electron density here than in the ketone and aldehyde cases. And then someone said, is electronics just hyperconjugation? Kind of. So electronics is a very, very broad term in chemistry. That's why I say it's the answer to everything. But for this case, we're looking at hyperconjugation, donating groups, and resonance. That's an awesome, oh my gosh, that's an awesome question. Does that make more sense? I don't remember who asked me to repeat it, but I hope it does. Cool. Okay, so wink, wink, nudge, nudge. This next question is really great for, you know, this class. It's good to know, especially if you can figure it out in condensed formula. Really good. Wink, wink. Sorry, I'm so caffeinated. Okay, so looking at what I just told you for the above order, I'm going to give you guys like 1 minute to just think about it yourself. I'm not going to make breakout rooms, but I want you to think about it yourself and try to figure out what the order would be from most to least reactive. And then you can do it, you can like say it in the chat, and you guys can unmute and talk about it if you want.
I can't see the first molecule. I don't know about other people. I don't know if it's my computer. Oh, okay. Oh, okay.
Better?
Perfect. Yeah, thank you.
You're welcome. Oh, also, I'm going to send you guys the attendance thingy because I forgot to do that.
I think I'm done. Can I like tell you what I got, but like privately?
Sure, you can do it in the chat.
Is there a way we could? Oh, in the chat. Okay.
Like you can select
Okay.
to send it to me privately.
Okay.
And I'll give you guys like 20 more seconds just to finalize whatever or do the attendance if you want to be off.
I'm gonna.
What was that?
I'm gonna put the. I'm gonna put like the how I numbered them. Like the first one, like I numbered them 1 through 5. 1 being most most reactive to 5 being least reactive.
Okay.
Or 6. I mean, sorry. Okay.
Okay. So I saw a bunch of people talking in the chat. Sorry, I can't talk and like type at the same time. Okay, so I saw a lot of people getting it right. So I think you guys have the general idea, and then if people didn't get it right, it was like very, very close. So does anyone want to volunteer, contribute, and be my assistant?
Can I be your assistant?
Sure. Or I say go ahead as if I told you what to do. So just give me like an idea of how you thought about it and why you chose what you chose.
Well, at first I was looking at which ones had like hydrogens, because it would have like least steric, and the fourth one had 2 hydrogens, and the second one had 1. So I presumed that the first one, number 1 would be number 4, and number 2 would be
Okay, let me actually do it like this because the numbers are kind of confusing.
Yeah, that's better. Okay, so I presume the first one would be with the one with the 2 hydrogens. The second one would be one with the 1 hydrogen, and then the rest is all steric hindrance. So the third one would be the ketone.
Okay, before you go on, you're right so far. I'm just going to interrupt you for 1 second. Because I want to ask everyone, we know that this is an aldehyde.
Yeah.
Anyone know what it's called when the aldehyde has 2 hydrogens?
Vicinal?
Wow, that was so fast. Formaldehyde. Formaldehyde. I might have spelled that wrong. That's fine though. So yes, so if you've ever wondered, this is formaldehyde. We use it, or we used to, I guess, for a lot of stuff. It's useful if you know this because sometimes he'll ask you and he'll just say formaldehyde instead of showing you. You know that is useful. That's all. Okay, go ahead.
Oh, okay. So I was at the steric hindrance. So like after the aldehyde and the formaldehyde, there's the ketone, and then after the ketone, there's no. I don't know if you're missing it. You're missing one on the screen. Could you zoom out a little bit?
Yeah.
Yeah, you're missing one more. Or no, never mind. Oh no, there it is. Okay. Yeah, so after the ketone, there's F, so it's E, F, A, B, or AC.
Yes, awesome. So once you get the aldehyde and ketone, it's just a matter of order of steric hindrance. So formaldehyde was first, and then we had our other aldehyde. Then we have E, F, A, and then C. Super, you guys are doing amazing. Any questions on what we've done so far?
So I did get it right. You told me I got it wrong in the private chat.
Oh, my bad. I literally.
No, you're good. I was just wondering. You were too caffeinated. Huh?
Nothing. Never mind. I just am all over
Too caffeinated.
caffeinated. Exactly. I mean,
I have
it's
a
good that you guys aren't in person because I also run around and hand out stickers. That is absolutely 100% true. And they were scratch and sniff and Halloween themed. It's so sad. I have so many stickers. Anyways, we're gonna move on.
I have a question.
Yes, please do.
Okay, so for like these, we literally just looked at steric hindrance and was able to determine. So is there an example where you have to look at both?
The first one is a good example. It doesn't get too much more complicated than that. If he
Okay,
asks
because
you to be, sorry.
I thought it would get like more competitive between them, and you really have to look at the electronics.
Yeah, exactly. It would be a lot more to consider. He's not going to do that to you though. He doesn't expect you to know like the nitty gritty details. You just have to know the general concept.
All right, thank you.
You're very welcome. So reduction. I love reductions because they're so much fun to do. Okay. They're like baby reactions. It's great. Alrighty. So it says it here, so I can't really ask you guys. But our two reducing agents are NABH4 and LiAlH4, which are both a mouthful. I want you guys to either guess, or if you've watched the videos or done whatever, let me know which one of those is strong. Please. Ooh, okay, and then which one do you think is weak? Ooh.
Is that one of your trick questions?
What?
Is that one of your trick questions? Because like I see both molecules, they both have like Na and Li, which are negative, and they both have 4 hydrogens and a halogen.
It's not necessarily a trick question. It's just one that a lot of people mix up all the time, and I have an easy way to remember it.
Okay.
So, I will tell you now. The one that is weak is NABH4, and the strong one is LiAlH4, or lithium aluminum hydride is the, what do you call it? LiAlH4, that's the name. And then NABH4 is sodium borohydride, or something like that. I don't remember. Yes. So, okay, now the way to remember it, right? The alphabet goes A, B, C, right? So A is before B. So aluminum is before boron. If that makes no sense to you, that's fine. Just you're going to hear me in your head screaming during the exam, A before B. So A is stronger than B.
No, that was my sister.
You're welcome.
Tutoring.
Kids. You guys are kids now. Sorry. Anyway, I don't know if you can even hear my sister. Whatever. I get too hyped about chemistry. Just ignore that. So, we actually have another reagent that Dr. West talks about. Do you know what it is? If you do, I'm going to be so excited. If you don't, that's completely fine. So PCC is an oxidizing reagent, but good guess. It has a really funny sounding name, and we call it Diba. Or sometimes it's called Dibol, but it's whatever. And the reason I spelled it wrong. I'm sorry. It's Diba. So the reason we write it in the middle, or I write it in the middle, is because it's both strong and weak. It's kind of like a middle. I like to think of it as a weak, strong agent. And the reason is because And I'm going to say this so I can write it down for you, and then I'll explain it. So don't freak out if you don't know what I'm saying. So diba is essentially only reacting with carboxylic acids and carboxylic derivatives, and it stops at the aldehyde. Again, I'll go over that in a few seconds, but I just wanted to have it written out for you guys. And so that being said, I want to add some information for NABH4 and LiAlH4. I'm sorry that I'm moving it around a little bit. I'm just kind of a perfectionist. So NABH4 is only going to react and I'm going to ask you guys before I write it down. So if it's a weak reagent, do you think it's going to react with the stronger electrophiles or the weaker electrophiles? Weaker, yeah. So the ones that are less reactive, aka the reason we did this just now, the reactivity list. This is a good time to kind of tell you the other thing I meant one more time. So the aldehyde and the ketone, we're going to call those group 1. And I'll actually move it over here. And we're going to call the carboxylic acids and derivatives, we're going to call them group 2. And the reason for that is group 1 is the more reactive and group 2 is less reactive, and group 2 also has oxygen. So that's the difference. I'm sorry if I'm going really fast. In my head, I feel like I'm talking really fast, but that might just be the coffee. So NABH4 is going to react only with group 1. NABH4 can react. Ooh, that was not nice. LiAlH4 will react with both groups. So I know I just said like a million words at once. Does it sort of kind of make sense? Do you have any questions?
Sorry, how would you describe group 1 without calling it group 1?
That's a good question. I'll write right here on the side as well. So group 1 consists of ketones and aldehydes, and it is essentially the more reactive group, aka the more electrophilic group, versus group 2 is carboxylic acids and esters. It is less reactive, or they are rather. And I'll move it over. I'm sorry, I'm writing over other text. And it is less electrophilic. I wish it didn't look like this. Okay, anyway, that's good enough. Does that kind of answer your question a little bit?
Absolutely.
Great. Oh, I forgot to mention, since I hadn't uploaded the handout yet for today's session, I felt like it was kind of unfair to you guys. Perfect is I'm gonna send you guys fill out version. Ta-da!
Are we done for today? 150?
The recording said 40 minutes, so I completely didn't even know what time it was. But yes, thank you for stopping me. I will. Today, it might take a little bit, it might get posted tomorrow morning. I will send an email with every. That's pretty much all I have. I'll stay here for a minute just in case you guys have any questions or anything. You guys did awesome. See you next week. Bye bye.